Hello, everyone. Today we're going to talk about ideal gases and the ideal gas law. First of all, let us define what is an ideal gas. So, as you can see here, an ideal gas approximation is that particles have negligible volume. So, the volume of the particles is zero, and they're in constant random motion, and there are no attractions between the particles, no interaction whatsoever. So intermolecular forces, they don't exist. The only interaction between the particles is just colliding, and that collision is perfectly elastic, which means all the energy from one particle when it hits the other is transferred. There is no loss of energy in this transaction. So the ideal gas doesn't really exist, although it is considered that gases approximate the ideal gas state at very high temperatures and very low pressure. And if you take a look at this is the base form of the ideal gas equation. So pressure multiplied by volume equals number of moles multiplied by the gas constant R, multiplied by temperature. Now, there are a couple of things here. So pressure is given in different units. Volume can also be given in different units, but moles are always moles. So it cannot be mass. It can be, but that's another type of equation. And temperature is always given in Kelvin. So you cannot use Celsius here. However, if you want to use atmospheres in this equation, then you have to use this value of the constant R. And basically, if you look at the units here, it basically tells you that which units you're using for which of these. And also, if you want to use torrs, then you have to use this number. And if you want to use pascals for pressure and cubic meters for volume, then you have to use this equation here, this constant here. Sorry. So these numbers are actually in your AP appendix, so you don't really have to worry about this at all. You just need to check the appendix, and you will find the formula and the units in there. Now, the trade-offs of these. So realistically, in questions, you will most often have a situation where one of these is constant. So either, as you can see here, if the number of moles and temperature are constant, then pressure is proportional to 1 divided by V. In other words, if pressure increases, then what has to happen with this? So pressure rises, the gas is squeezed, so volume decreases. And you can see like most of the possible situations here when N and P are constant, then V is proportional to T, P and T are constant, then V is proportional to N. And here we have just a graphical representation of these things. So P and 1 through V are directly proportional, right? V and T are directly proportional, but P and V are not directly because P is directly proportional to 1 divided by V, right? So, I mean, these are not that important because I will show you how to do this without memorizing all this. So, this is how you do this. So, you don't really have to remember all this because you can just derive all this from the ideal gas formula from this. How do you do that? Well, you just remember PV equals nRT. And then this is just base math. So if P and T are constant, then you just move P and T to the same side of the formula. You just basically move all the constants to the same side of the formula. So you move P and T and R because R is always constant, right? So you move P and T and R to one side of the formula, and that is constant, and then that will equal whatever remains of the formula, right? So P divided by TR will be equal to N divided by V, right? Because these are the only two things that are not constant. And therefore, if I increase the N, I will also have to increase the V because N1 divided by V1 will be N2 divided by V2. So in other words, N and V are going to be proportional. In calculations, this is a good form to use. I mean, this is not ideal for using calculations. So you're going to use this form more often than not. And then the other situation, if v and n are constant, again, you just move all the constants to the left side of the formula, and you get nr divided by v equals p divided by t. And therefore, again, p is proportional to t because this has to stay constant. So if I increase p, I also have to increase t. So they are proportional, which you can see here. So it's the same thing, just written in a different way. That means that P1 divided by T1 equals P2 divided by T2, or P times T equals constant. Or you can even write it in a like it is in previous slide. And then PV equals nRT, and N is constant, so only N here, and of course R. So NR equals PV divided by T, which means PV divided by T will be constant, which means this, and so on. You can do this in any combination. So one more time, you just take everything that is constant, you move it to one side of the equation, and whatever is left will tell you what actually happens. I mean, if I look at this, if I increase the number of moles, what has to happen with V in order for N divided by V to remain constant? So if I double number of moles, I also have to double the volume, right? Because the formula tells me that this has to remain constant, right? If I increase the P, what has to happen with V? Has to decrease for this to remain constant. So it is a very simple mathematical expression, and it makes you able to do this without memorizing. Now, this is also something that comes from that equation. Is just a better representation, a more structured representation. So if n and t are constant, then p1 equals v1, p1 v1 equals p2 v2. And there's a typical scenario, which is what I specifically like. So they will not tell you actually in the questions n and t are constant. You're going to have to derive that from the question. So if you look at this, a syringe compressed at room temperature. So temperature is constant, and whatever is in the syringe, so number of moles stays the same, right? You're compressing it, so the pressure and volume are going to change. A balloon warmed in the sun. So again, N and P are going to be constant. A sealed, rigid can, which is heated. When they tell you rigid, you should know that that's like a code for V being constant, and it's sealed, so N is constant. A balloon, again, because it's closed up, N is still constant. In a lot of the questions, you will see that N will remain constant. So you will have other examples of this, and you're going to basically have to derive it by yourself, but it's not very difficult. Now, if there is a mixture of gases, we have a bit of a special situation, but this is very easy to do, and it can be done in multiple ways, which is why I like it. So uh, let's say it like this. So 1 mole of any gas always exerts the same pressure. So that means if I have a total pressure of 1 atm, and inside is the mixture of 50% oxygen, 50% hydrogen, equal amount of moles. This is not about mass, this is about moles. So I have 50% moles of oxygen, 50% moles of hydrogen, and my total pressure is 1 atm. Partial pressure of oxygen will be 0.5 atm, and hydrogen also 0.5 atm. What does that mean? Well, the fraction of the gases, 0.5, is their impact on pressure. So the total pressure equals partial pressures of each gas. So if I got oxygen exerts 0.1 atm, and then nitrogen 0.2, and then hydrogen 0.3, then my total pressure is going to just be 0.6. But that also means I have the number of moles of this to this to this is 1 to 2 to 3. So if partial pressure of something is 1 and the other thing is 0.5, then their molar ratio is 1 to 0.5, or 2 to 1, if you will. So you can see that in here, and you will see when we start doing examples that this is pretty easy and very comfortable to do. And there are multiple ways to do it, so it's difficult to make a mistake. And then there's also density. This is something that they don't give that much. As you know, density is mass divided by volume, and also number of moles is mass divided by molar mass, right? So if you plug that in, and d being density, you will see that actually you can basically take this m, put it in here, and then plug this n into the ideal gas equation, and therefore use density instead of the number of moles sometimes if you have enough data. Again, you will see in the examples this is pretty easily done and not that common. Also remember this. So at standard temperature and pressure, 1 mole of each gas always takes this volume. So 1 mole of any gas is always 22.4 liters if the temperature is 0 degrees Celsius and 1 atm. So if you increase the temperature, that changes a bit, as you can see here. Yeah, be careful of mismatched units. Again, the units of R change, so make sure you check your appendix, your AP appendix, and plug the correct units in. Now let's do some examples. My favorite part. So a steel cylinder holds 2.75 mole of helium at 11 degrees Celsius and a pressure of this many torrs. What volume does the gas occupy? So this is basically just plugging this into the ideal gas equation. So PV equals nRT. I have the P. Yeah, they converted it here in ATM, but you can also use torrs if you want to use the correct number for R from your AP appendix. But however, you always have to convert temperature into Kelvin. So watch this one. You don't know the volume, right? So basically, you need to flip the ideal gas equation to this form: V equals nRT divided by P. And then you got all of these from here, and you can just calculate. Pretty easy and comfortable. A weather balloon holds this many liters of helium at 1 atm and 22 degrees. It rises to an altitude where pressure is. So now we got lower pressure and different temperature. No gas escapes, which means the number of moles is standard. What is the new volume? So this is where you actually use what I taught you about flipping the equation. So basically, I got one volume and one pressure and one temperature, and then another volume, another temperature, and what is the pressure. So basically, N and R are constant here. So NR equals P1 V1 T1, or you can just say PV divided by T. And therefore, P1 V1 divided by T1 equals P2 V2 divided by T2. And you can just plug all this in, and you will find that you can easily calculate V2. Or you can do it in the way that is done here, slower but more methodically. A rigid 2-liter vessel at 25 degrees Celsius contains 0.4 grams of N2 and 3.2 grams of O2. Now you have grams here, but remember, you can always use the periodic table. You can turn this into moles very easily. Calculate the partial pressure of each gas, the total pressure, and the mole fraction of nitrogen. So the mole fraction is just the number of moles of nitrogen divided by the total number of moles. So remember what we learned. So fractions are better used than percentages. So how do you do this? So these are the masses. You divide this by molar mass. Remember, it's N2 and O2. It's not N and O. Gases are always 2. So 0.5 moles is nitrogen and 0.1 moles is oxygen. And in total, the pressure is, the number of moles is this, and the pressure is 1.83. Now, how do I know this? Well, I can calculate from PV equals nRT. I will calculate the total pressure, right? How will I calculate? Well, I have number of liters. I have here temperature. I have the total number of moles, right? So I can calculate the total pressure from here because I have all the data that I need. So when I calculate the total pressure, 1.83, I will know that out of that total pressure, 1.83, 33.3% is nitrogen and 66.6 is oxygen. Why? Because the number of moles is zero point 0.1 to 0.05, which means this is 2 to 1, right? And my total pressure is this. So I can just take the partial, the mole fraction. So calculate the mole fraction and then just multiply this with the total pressure and I will get 0.33. So this can be done in other ways too, but this is the easiest way. So you just calculate again the number of moles, total number of moles, so mole fraction of N2 is 0.33, and then how much pressure it exerts is just multiply this with this, and you'll basically get that number. Okay, 0.428 gram sample of gaseous compound occupies. Okay, so we got mass. We don't have moles and we don't know which compound, so we can't calculate moles. But we have volume, we have temperature, we have pressure. If we have moles, temperature, and pressure, we can calculate M. So this is just plugging into the equation. So you flip the equation. So because you have P, you have V, you have T, and you know R, so you can easily calculate the number of moles. This is the number of moles. Now, the molar mass of the compound, as you know, is mass divided by number of moles, right? So molar mass is grams per mole. I have grams here. I just calculated moles, and I plug that in. I get the molar mass, and I can even try to figure out which compound this is. Zinc reacts with hydrochloric acid like this. What volume of hydrogen measured at 24 degrees Celsius and this many ATMs is produced from 3.27 grams of zinc. So this is a little bit of a stoichiometry that we have going on here. So first you calculate the moles of zinc using molar mass, so this many moles. And then you use the molar ratio because you know that 1 mole of this gives us 1 mole of hydrogen. So if we got this many moles of zinc, we also going to have this many moles of hydrogen. And then you can just calculate the volume because you know that for any gas, 1 mole is 22.4 liters. You can just do that. Or here, I mean, actually, you can't because here they gave you the temperature. I apologize. So if the temperature were 0 and pressure 1 atm, you could use the fact that each gas takes 22.4. But here you just need to plug this data into the equation, the ideal gas equation, we get the solution. Okay, this one is a bit cheeky. So hydrogen gas is collected over water at 22 degrees Celsius. The sample collected occupies 245 milliliters, and the total pressure inside is 248 torr. The vapor pressure of water is 21.1 torr. How many moles of hydrogen were collected? So there is hydrogen gas above here, but there's also water, and the vapor exerts this much pressure. And in total, I have this much pressure. So I have to go this minus this in order to figure out that part of pressure that comes from hydrogen. So that's this many torrs, and then they just converted it into ATMs. Mostly people want to use ATMs because that's most commonly given in AP curriculums. And now you just need to plug that into the ideal gas equation because you've got the volume, got the temperature, and you know the N because it's actual N is what you have to calculate, but you know the P. So you can just calculate N from the ideal gas equation. A rigid sealed vessel at constant temperature contains 0.4 moles of NO and 0.2 moles of O2 at a total pressure of 1.5 atm. The reaction goes to completion. Predict the final pressure and explain the change. So basically, this is very commonly given like this. Seems confusing, but it's really not. So if I got 0.4 moles of NO and 0.2 moles of O2, and I see the reaction tells me that NO and O2 react 2 to 1. What does that mean? from 2 moles of this and 1 mole of this, I'll just get 2 moles of NO2, which means from zero point 0.6 moles total, I will actually get just zero point 0.4 moles remaining, which means the number of moles of gas in here will be reduced by 50%. If I reduce 1.5 by 50%, I'll just get 1 atm, right? So I don't even need all this. I don't even need all this. Again, I know zero point 0.4 and zero point 0.2 are going to give me zero point 0.4 of this, right? Because it's 2 plus 1 gives me 2. So zero point 0.4 plus zero point 0.2 gives me zero point 0.4. So instead of having zero point 0.6 moles of in total of gas, I now have zero point 0.4 moles in total of gas. So that is basically this. It's 50% less. So it's now 1 atm. And this one is just recognizing the graphs. It's not, I mean, it's not even that. It just tells you which of the plots below is a straight line passing through the origin. The origin is just, it's just zero here. They will give questions like this sometimes in AP where you simply have to, read the graph. And that would be everything for today. Practice and let me know if you need any help. And bye bye.